All right, what I want to do now is an example to show you the strength of some of the results that we were just talking about. And what I want to do is I want to compute the integral of 1 over z, where gamma is going to be the piecewise smooth curve. So it's continuous piecewise smooth curve around the square with vertices 1 plus I, 1 minus I, negative 1 minus negative 1 minus I, and negative 1 plus I. So it's going to be the path around here. It'll be in the counterclockwise direction. And what I want to do is I want to compute the integral of 1 over z over gamma, where gamma is this path, okay, over the rectangle. And what we could do is we could break gamma up into, say, 4 pieces. So we could write gamma is the union of 4 curves. So let's call this gamma 1, gamma 2, gamma 3, gamma 4, and compute the integral over all of these pieces. This U stands for union. And what we're going to do is we'd have to compute, so the integral over gamma is going to be the integral over gamma 1. I'm just going to use some shorthand here, plus the integral over gamma 2, plus the integral over gamma 3, plus the integral over gamma 4. And I would strongly encourage you to actually write all this out. I'm going to do the first one for you. So I'll show you that the integral over gamma 1, and I'll show you how that works, is going to be some value. And the way that we're going to do this is we're going to have to come up with a parameterization that's going to take 1 minus I to 1 plus I. And so let's write gamma 1 of t as, let's see, let's call it 1 plus I t, where t goes from negative 1 to 1. Okay, so that's gamma 1 of t. And just by definition of the line integral, what we're going to do is we're going to write this integral as the integral from negative 1 to 1, because those are our bounds for the parameterization of gamma 1. And we're going to compute f of gamma times gamma prime. So f of gamma means we're going to take gamma and plug it into z. So this is going to be 1 over 1 plus it times the derivative of gamma, which is going to be the derivative of 1 plus it is going to just be I. Okay, so it'll be 1 over 1 plus it times I dt. And so this is going to be a straightforward integral to evaluate now. So this is going to be the integral of, let's see, we're going to have the natural log of, well, I need to be a little bit careful here. Say the principal value of the natural log of 1 plus I t divided by I, but we had the times I from before, so it can just be that, evaluated from negative 1 to 1. So that's going to be, let's just use the principal branch is fine. So this is going to be the log of 1 plus I minus the log of 1 minus I. And let's see what that's going to be. That's going to give us the natural log of the absolute value of 1 plus I times the argument of 1 plus I, and then minus the natural log of the absolute value of 1 minus I minus I times the argument of 1 minus I. And so this is going to work out to be, if I do this correctly, this is going to work out to be pi over 2. So let's think about how this will work. This will be pi over 2i. So the natural log, so the modulus of 1 plus I is going to be square root of 2. So this is going to work out to be pi I over 2. And the other parts should cancel. Okay, so that's going to be pi I over 2. And you should get a similar value if you add up all the other parts. You just have to be a little bit careful with the branch that you're using of the logarithm, but this should work out. And it turns out when you integrate all of these, you'll end up with pi I over 2 times 4. And it turns out that this entire integral is going to be 4 times 1/2 pi I. So in other words, 2 pi I. Okay, and so that's how you would evaluate this integral over the unit square. But notice that if I look at this function f, okay, and I think about this function is going to be holomorphic over the entire complex plane except at 0. So what I want to do is I want to think about what's another simpler curve that we could change gamma into. We could homotopically translate gamma into some other curve. As long as it doesn't have to cross over 0, then everything's fine. So for example, you couldn't homotopically translate this square into a curve that looks like this because now the origin's not inside that new curve. But you could translate it into, say, the unit circle, and that's a much nicer curve. And so it turns out that those will be equal as integrals. So a much easier way to do this is to notice that the integral over that square is going to be the same as the integral over, I'm going to call it gamma naught, where gamma naught is going to be the unit circle gone counterclockwise. So gamma naught is going to be e to the it, where t goes between 0 and 2 pi. And this is an integral that we've already calculated. We know that this integral is 2 pi I. We have to do much less work. Okay, so this integral is 2 pi I. We have to do much less work. And we know that by Cauchy's theorem, these are going to be equivalent. And indeed, it turns out these are exactly equivalent here. Okay, so we get the same value either way. We get that this integral is going to be 2 pi I. But once you make this choice, once you figure out that you can actually change the path itself, and that really drastically simplifies the integral, we can use this to our advantage to do some kind of complicated integrals much easier now.